Angular momentum selection rules in beta decay. We already discussed about beta decay, its energy distribution, etc. So in order to, when a nuclear reaction or beta decay is taking place, it have to obey certain conservation rules. We know that total energy is conserved, angular momentum is conserved. So angular momentum have to be conserved in a beta decay. That is the total angular momentum before decay. That is the angular momentum of the parent should be equal to the total angular momentum of the daughter and the angular momentum of the particle which are emitted by the nucleus. That is protons and emitted particles is electrons and neutrinos. So the total angular momentum of the neutrino electron pair plus the angular momentum of the daughter nucleus should be equal to the angular momentum of the parent. Suppose let us examine a decay process. So gallium 3166 converted into zinc 3066 with positron emission along with an antineutrino. So this is the nuclear state of the parent nucleus. The parent nucleus is represented by I pi p parent gives I pi daughter plus the total angular momentum of the electron neutron pair. The term is here, so it is missing this, so you have to, no, this will indicate the change, that is from parent to daughter. Parent is converted into a daughter. Okay, so here I is the total angular momentum of the parent nucleus. What is total angular momentum of the nuclei? Total angular momentum of the nuclei is the vector sum of the orbital angular momentum plus spin angular momentum, J plus S, values of the parent nuclei. നിങ്ങൾക്കറിയാം പഠിച്ചിട്ടുണ്ട് ഷെൽ മോഡൽ ഓഫ് ദ ന്യൂക്ലിയസ്. അതിൽ ഇലക്ട്രോണിക് ഷെൽ പോലെ തന്നെ ന്യൂക്ലിയസും ഷെല്ലിലാണ് പ്രസൻറ്റ് ചെയ്യുന്നത്. അങ്ങനെ വരുമ്പോൾ അതിനൊരു ഓർബിറ്റൽ ആംഗുലർ മൊമെൻറ്റവും അതിനൊരു സ്പിൻ ആംഗുലർ മൊമെൻറ്റമാണ്. ന്യൂക്ലിയസിൻ്റെ ഓർബിറ്റൽ ആംഗുലർ മൊമെൻറ്റം പ്ലസ് സ്പിൻ ആംഗുലർ മൊമെൻറ്റം ഈസ് ദ ടോട്ടൽ ആംഗുലർ മൊമെൻറ്റം ഓഫ് ദ ന്യൂക്ലിയസ്. സോ ഇവിടെ ഐ എന്ന് പറയുന്നത് ടോട്ടൽ ആംഗുലർ മൊമെൻറ്റം ഓഫ് ദ ന്യൂക്ലിയസിനെ റെപ്രസെൻറ്റ് ചെയ്യുന്നു, പാരന്റ് ന്യൂക്ലിയസ്. അതേപോലെ ഇത് ഐ എന്ന് പറയുന്നത് ടോട്ടൽ ആംഗുലർ മൊമെൻറ്റം ഓഫ് ദ ഡോട്ടർ ന്യൂക്ലിയസ്. ഇവിടെ പാരന്റിൽ നിന്ന് ഡോട്ടർ ന്യൂക്ലിയസ് ഉണ്ടാകുമ്പോൾ ഇതുപോലെ ചേഞ്ച് ചെയ്യുന്നത്. പൈ എന്ന് റെപ്രസെൻറ്റ് ചെയ്യുന്നത് പാരിറ്റി ഓഫ് ദ ന്യൂക്ലിയസ്. പാരിറ്റി എന്ന് പറഞ്ഞതെന്ന് വെച്ചാൽ അതിൻ്റെ മിറർ റിഫ്ലക്ഷനെ കാണിക്കുന്നതാണ് ഒരു ന്യൂക്ലിയസിൻ്റെ പാരിറ്റി. അപ്പോൾ പാരിറ്റി ചേഞ്ച് ഈസ് റെപ്രസെൻറ്റഡ് ബൈ ദ -1:L. സോ ഇതാണ് ഒരു ന്യൂക്ലിയസിൻ്റെ പാരിറ്റി എന്ന് പറയുന്നത്. അപ്പോൾ ഇവിടെ നമുക്കറിയാം ഇതിന് നമുക്ക് ഇങ്ങനെ റെപ്രസെൻറ്റ് ചെയ്യാം. I pi p gives I pi daughter plus J E nu. J is the total angular momentum of the electron neutrino product. That is the total angular momentum of the particle which are coming out of the nucleus. So ഒന്നുകിൽ ന്യൂക്ലിയസിന് ഒരു പോസിറ്റീവ് പാരിറ്റി ഉണ്ടാവും അല്ലെങ്കിൽ നെഗറ്റീവ് പാരിറ്റി ഉണ്ടാവും. അതാണ് പോസിറ്റീവ് പാരിറ്റി പ്ലസ് there are two choices, positive parity plus and negative parity minus. Parity positive means they look similar after mirror reflection, and parity negative means both are different in their image, particle and their image are different, so have the negative parity. So when a nucleus is changing from parent to daughter, if there is a change in parity, that is represented by minus 1 raised to L. If L is a 0 or even number, this minus 1 raised to L is equal to 0. So delta pi, change in parity is given by, suppose പാരന്റിനും ഡോട്ടറിനും ഒരേ പാരിറ്റി ചേഞ്ചിട്ടുണ്ടെങ്കിൽ here the parent have positive parity and daughter have negative parity. അപ്പോൾ രണ്ട് പോസിബിലിറ്റിയാണ് ഡെൽറ്റ പൈ can take two values if there is a change in the parity and if there is no change in parity. Change in parity means parity of parent is changes into parity of the parent is different from that of the daughter nuclei. So suppose parity changes from plus to minus, and parity can also changes minus to plus. That means when there is a change in parity, L value must be odd number 1, 3, 5, etc. if there is a change in parity, because that is equal to minus 1 raised to L. Suppose if there is no change in parity, the L value may be 0 or plus 2, plus 4, etc. So for 0 and odd numbers, this parity change is there is no parity change, that is parity change is 0. If the nucleus initially have the negative parity, its final parity daughter nuclei also have the negative parity. If the particle have positive parity, it's if the parent nuclei have the positive parity, the daughter nuclei also have the positive parity. That means there is no change in parity. Change in parity means its parent nuclei have plus pi value and the daughter have minus pi value. So there is a change in the parity, that is from parent plus to daughter minus, or minus parent to daughter plus. So these represent the change in parity, and this represent if there is no change in parity. So here, so let us consider the example of gallium 3166 to zinc 3066. This state is already given. Question paper is state down. That is gallium has 0 plus state and zinc has 0 plus state. So 0 plus state to 0 plus state. So we have to find out which type of transition is this, and we know that the parity, total angular momentum I pi of parent is equal to I pi of the daughter plus j e nu. The wave function is given by, thus already discussed, that electronic or nuclear wave, electronic or neutrino wave function psi I or psi nu is given by 1 by square root of v into 1 plus I p dot r by h bat plus I p dot r the whole square by h square, etc. So for a reaction to take place, the change in parity or change in angular momentum should be taken away by this. Then only this reaction possible. So the total angular momentum before collision should be equal to total angular momentum after collision. So this change in angular momentum should be taken away by this neutrino electron pair. So that is the basic theory behind the selection rule. One important thing is parity change is minus 1 raised to L, right? Pi is equal to minus 1 raised to L. So when will be this wave function is equal to 1 by square root of v? When r is equal to 0, this term will vanish, and psi or psi nu is equal to 1 by square root of v. So this approximation we already discussed while we discussing the theory of beta decay. This is an approximation, and this is an allowed approximation. So this is known as this, when r is equal to 0, or we approximate psi or psi nu is equal to 1 by square root of v. That is for r is equal to 0. then that type of beta decay is known as the allowed beta decay. So we are taking the wave function at the origin. Electron or electron neutrino are created at the center of the parent nuclei. From there they are coming out. So from that expression we can understand that the wave function at the origin, we are taking the wave function at the origin, and also the electron neutrino are created at the center of the parent nuclei. From there, from the center they are coming out. So we do this approximation in the case of Fermi expression by taking electron and neutrino wave function to be constant. Essentially, we have committed that the orbital angular momentum of this particle is a constant. This particle means this outgoing particle, that is the electron neutrino pair. So their angular momentum with respect to daughter nuclei is 0. And the electron and neutrino have spin angular momentum half. They can either combine together in two ways. If their spins are parallel, this half plus half 1. If their spins are anti-parallel, half minus half 0. So S can take two values, half plus half and half minus half. So here also we are discussing the same thing. At r is equal to 0, this electron and neutron pair cannot take away any angular momentum. So the only change in angular momentum, so the change in the angular momentum of the nucleus must result from the spin of the electron and neutron. Each of these have a spin half values. These two spin can parallel at that time s is equal to 1 or anti-parallel at that time s is equal to 0. If the spins are anti-parallel, we call that decay as Fermi decay. So we called, when L is equal to 0, we call that decay as allowed decay. It is a technical term. Not all allowed decays are physically allowed. Anyway, when L is equal to 0 situation are taken, we call it as an allowed transitions. And if the spins are anti-parallel, or when S is equal to 0, if the spins are anti-parallel, we know that we call that transition as Fermi decay, or a decay process. That decay process is Fermi decay. Then in allowed approximation L is equal to 0, there cannot be any change in the nuclear spin. So for delta I is equal to I minus I. This is the sum of initial angular momentum plus final angular. So that is equal to 0 because this transition taking place from 0 to 0. So in allowed Fermi decay, L should be equal to 0 and S should be equal to 0, where spins are anti-parallel. So when the S is equal to 1, if the electron and antineutrino have same spin, they call that type of decay as gamoteller decay. When L is equal to 0 and S is equal to 1, we call that decay as allowed gamoteller. When L is equal to 0 and S is equal to 0, we call that type of decay as allowed Fermi decay. So if the spin are parallel, the electron and neutrino spin are parallel, its total spin angular momentum S is equal to 1. At that time, they will take away the spin difference between the parent and daughter nuclei by 1. Okay. So in the allowed approximation, they means the daughter nuclei or the particle which are, they means the particles which are coming out carry a total angular momentum of 1 unit. Thus, I initial and IF must couple together through the vector length. I is equal to IF plus 1. This is nuclei, initial nuclei. This is final nuclei. This is the total angular momentum of the two. That is total angular means total spin angular momentum of this neutrino electron pair, or it is the total angular moment of neutral electron pair because L value is 0. So this is possible only if delta is equal to 0 or 1. Okay, this reaction is possible only if delta is equal to 0 or plus 1. And if delta I if the electron and neutrino pair carry no orbital angular momentum, then the parity of the initial and final state must be identical, since parity associated with the total angular momentum L is equal to minus 1 raised to L. So the selection rule for allowed beta decay are delta I is equal to 0, 0 or 1, or the parity change delta pi, there should be no parity change, is equal to 0. So in all allowed approximation L is equal to 0, and for Fermi decay S is equal to 0, and for Gamma-Teller decay S is equal to 1. Okay. So if L is equal to 0 and S is equal to 1, L is equal to 0 and S is equal to 1, this is the condition. So this initial nuclei angular momentum is equal to final nuclei total nuclei angular momentum plus the total angular momentum of the electron neutron pair. So here IP is equal to ID plus 1, because if for S is equal to 1 and L is equal to 0, L plus S is equal to 1. So this IP can vary from ID plus 1 to ID minus 1. So if ID is equal to 0, this IP can vary from 2 plus 1 to 2 minus 2 plus the with the difference of 1. Here 2 plus 1 is 3, 2 minus 1 is 0. So 1, 2, 3 in between numbers can be considered. So 1, 2, 3 integers. So this S is equal to 1 approximation is or decay process is known as the Gamma-Teller decay. So when L is equal to 0, S is equal to 1, we call this is an okay, let us consider some example. O14 gives N14, its transition is 0 plus to 0 plus. So delta E is 0 plus 0 plus 0 to 0 minus 0, that is 0. Delta I value is equal to 0. Then what about pi? Pi, there is no change in pi. So delta pi is equal to 0 because 0 plus 1 plus 1. So delta I is equal to 0. Now parity. So this is this reaction is a pure Fermi reaction. So CS delta is 0 to 34 to S. So this case the parity change. So delta I is equal to 0 and delta pi change in parity is 0. So this is a delta I is equal to 0 and delta pi is equal to the parity change is equal to 0. In that case L is equal to 0 and S is equal to also 0. So this is a pure Fermi transition or allowed Fermi transition. Similar in the case of Cl34, S34, it's or carbon 10 to boron 10, this 0 plus to 0. Okay, that is a positive transition from 0 plus to 0 plus. So in this case delta pi both are 0, 0. Delta I, there is no change in parity, so delta I is equal to 1. So it is This reaction is known as the allowed Fermi reaction. Okay, let us consider another example, helium 362, lithium 6. Third example, helium of atomic number 2. 62, lithium atomic number 36. It's also transition is 0 plus 2, 1 plus. So when we change the dye, change in the angular momentum of the nucleus. So this change in angular momentum is taken away by the neutrino electron pair. So this is 0 plus 1 to 0 minus 1. So the answer is 1. 1. So 1, and there is no change in parity. That is L is equal to 0 here. When L is equal to 0, S is equal to 1. So then only delta is equal to 1. So pi is equal to 0. So minus 1 raised to L. So minus 1 raised to 0, that is equal to 0. So when the second condition, so we are taking the value j is equal to 1. So j is equal to, we fix to L value. L in the value fix ചെയ്തു, L in the value 0 വരണം, കാരണം parity change ഇല്ല. പിന്നെ നമ്മൾ S ന്റെ കാര്യമാണ് നോക്കുന്നത്. L 0 ആണെങ്കിൽ S എന്ത്, J 1 വരണമെങ്കിൽ S എന്താവണം, 1 ആവണം. എന്നാലേ 1 plus 0 അല്ലെങ്കിൽ 1 minus 0 1 ആയിട്ട് വരും. അപ്പോൾ J 0 ആകുമ്പോൾ S എന്തായാലും 1 വന്നേ പറ്റുള്ളൂ. എന്നാൽ മാത്രം J is equal to 1 എന്ന് പറഞ്ഞ കേസ് ഉണ്ടാവുള്ളൂ. So this is condition is J is equal to, condition is L is equal to 0, S is equal to 1. So this is known as the allowed. Allowed means L is equal to 0. Gamotilla, S is equal to 0. So let us consider another example. Boron 13 to carbon 13. So these are all allowed transitions. Here the transition from 3 by 2 minus to half minus. So what is change in the dye or the change in the angular momentum of the daughter? Electron neutrino pair, that is 3 by 2 plus half to 3 by 2 minus half. So what is 3 by 2 plus half? That is nothing but 2. 3 plus 1, 4 by 2, 2, and 3 by 2 minus 1 by 2, that is 2 by 2, 1. So in difference there is no number 1 and 2. So the possible value of the dye is 1 and 2. And when we check the parity, there is no change in parity here. So L is equal to 0. So there is no change in parity. So delta pi is equal to 0. So L is equal to minus 1 raised to 0. So 0 means there is no change in parity. Okay. So this transition, L is equal to 0 and I value 1 or 2. So we are taking the minimum angular momentum condition 1. So when will be, so total angular momentum ഒന്ന് വരണമെങ്കിൽ L is equal to 0 ആണ്, S എന്തായിരിക്കണം, 1 ആവണം. L ഓൾറെഡി നമ്മൾ പറഞ്ഞു പാരിറ്റി ചേഞ്ച് ഇല്ലാത്തതുകൊണ്ട് L എന്തായിരിക്കും, 0 ആയിരിക്കും. അപ്പോൾ L plus S ആണ് ഈ പറയുന്ന ചേഞ്ച് ഇൻ ആംഗുലർ മൊമെന്റം. അപ്പോൾ S എന്താവണം, 1 ആവണം. Okay, so S is equal to 1 is an allowed gamma.